December 2nd, 1940. Hatfield Aerodrome, Hertfordshire. The factory air hangs with the smell of sawdust and casein glue. Wooden frames line the assembly floor like the ribs of unfinished ships. Men and women in aprons move between benches, their hands powdered white with balsa dust. Outside, the sky carries the dull pulse of distant bombers heading north. Each vibration through the corrugated roof feels like a reminder metal is now a luxury Britain cannot afford. Under the canvas of Hangar 2, a new fuselage rests on trestles. No rivets. No aluminum panels. Only a seamless shell of birch plywood and Canadian spruce, curved into form by the heat of steam presses. The engineers move quietly, aware that every sound carries in a room built for secrecy. At the center stands Geoffrey de Havilland, inspecting the surface where two halves of the fuselage meet. A thin man in wire-rimmed glasses, he traces a line along the wooden skin. The adhesive beneath, a newly refined casein resin, has bonded the structure with no visible join. According to the design sheets pinned on the wall, the aircraft's projected weight is under 14,000 pounds, nearly half that of the RAF's Wellington bomber. Its shape, smooth and clean, is meant to cut through the air with minimal drag. The draft notes call it D.H.98. The workers, quietly skeptical, call it the plywood folly. A supervisor walks past the wing jigs, checking alignment with a metal ruler. The wings are one continuous curve, free of bracing wires or protrusions. At their center, wooden spars taper into the nacelles where two Rolls-Royce Merlin engines will be mounted. Nearby, a mechanic polishes the propeller hubs, blackwood, not metal. Even the propeller blades are laminated ash. The machinery hums with the rhythm of an experiment, wartime production married to peacetime craftsmanship. Across Britain, the Air Ministry debates the practicality of the concept. Intelligence memos from Whitehall describe it as an unnecessary diversion of materials better suited to furniture than flight. Yet here, in Hatfield, the design team persists. The idea is simple: a bomber fast enough to outrun fighters does not need heavy armor or defensive guns. De Havilland calls it speed as protection. At midday, a test crew hauls the fuselage toward the assembly bay. The sunlight through the open doors glints across the polished wood, turning it almost golden. No rivet lines, no exposed seams, a surface smoother than any metal airframe. A junior officer from the ministry takes notes in silence, recording the progress of prototype W4050. The notation is brief, structure intact, finish excellent, appearance unorthodox. By dusk, the prototype stands complete, its twin engines awaiting installation. Workers sweep sawdust into piles while inspectors move along the fuselage with flashlights. The quiet is broken only by the hiss of steam from the curing press. No one applauds, there is no ceremony. Outside, the blackout curtains are drawn. The war continues overhead, unseen. In the control office, de Havilland signs the day's report. The ink is neat, deliberate, airframe complete. Awaiting engine fitting and taxi tests. He closes the logbook, extinguishes his lamp, and pauses at the doorway. Through the glass partition, the wooden aircraft glows faintly under the factory lights. It looks fragile, almost like a child's toy. Yet its shape hints at something faster than belief. According to later accounts from the Hatfield engineers, that night marked the quiet beginning of the most unconventional aircraft project in wartime Britain. Built not from metal, but from the same materials as furniture and violins. Designed not for durability, but for speed and silence. A bomber that would one day fly higher, farther, and faster than any German fighter then in the sky. January 1941. The doors of Hatfield's test hangar open to frost and low winter light. Mechanics in leather coats push the wooden airframe out across the tarmac, its pale surface reflecting the overcast sky. A thin mist gathers around the twin Merlin engines, still untested. A ground crewman checks the magnetos, his breath visible in the cold. The aircraft rests at the runway threshold, no gun turrets, no armor plate, only smooth plywood and the faint scent of glue. Flight engineer John Walker records the startup procedure on a clipboard. Fuel pressure, manifold vacuum, magneto timing. The first engine coughs, then settles into a rolling rhythm. The second follows, the propeller blur merging into one continuous note, a clean mechanical tone, lighter than expected for a bomber. The sound carries across the airfield, drawing technicians from nearby bays. They pause, curious, as the wooden prototype begins its taxi tests. From a distance, the D.H.98 seems to skim over the ground, its undercarriage flexing lightly on the frozen surface. De Havilland observes through binoculars, noting how the fuselage vibrates under torque but shows no structural distortion. The adhesive seams hold. The wooden frame behaves like a single mold shell. Monocoque integrity confirmed, the test sheet later reads. Inside the cockpit, pilot Geoffrey de Havilland Jr. checks the instrument panel, a compact cluster of gauges, pressure dials, and the early oxygen system. No armor glass, only thin perspex giving wide visibility. He eases the throttle forward. The Mosquito rolls smoothly, lifting a faint trail of frost behind its wheels. The airframe responds with the balance of a much smaller aircraft. Onlookers remark that it moves like a fighter disguised as a bomber. At 70 knots, the tail lifts. The aircraft gathers speed quickly, then, almost without effort, leaves the ground. The stopwatch on the ground cruise table marks 12 seconds from start to flight. No shake, no stall warning. It rises straight and steady into the grey. The sound fades, leaving only the hum of distant engines and the ticking of watches. In the observation hut, the Air Ministry inspector writes a terse comment in his logbook, initial flight characteristics positive. No tendency to yaw or flutter. Exceptional climb. He underlines exceptional. That single word later appears in every internal report. The flight lasts 23 minutes. When the Mosquito returns, the descent is shallow, confident. The landing gear touches down lightly, as if the aircraft weighs far less than recorded. Mechanics rush to inspect the wings and joints. No cracking, no delamination. Every panel remains flush. The adhesive, a synthetic urea formaldehyde resin later called aerolite, has proven its strength. The next morning, engineers begin systematic testing, stress loading of the wings, deflection under G-force, surface resonance at different throttle levels. The results show what few believed possible: the wooden structure absorbs vibration more efficiently than metal, reducing fatigue and maintaining aerodynamic smoothness at high speed. In the drafting office, performance figures are penciled beside comparison charts. Projected maximum speed, 382 miles per hour. Standard RAF bomber average, 265 miles per hour. The numbers are circled in silence. By February, word spreads quietly through the Air Ministry that de Havilland's plywood aircraft has exceeded the speed of Britain's fastest fighter, the Spitfire Mk2, at low altitude. Yet official endorsement remains cautious. The RAF's doctrine favors heavy bombers with defensive turrets and large crews. The Mosquito carries none. Its concept, unarmed, relying on speed, runs against established logic. At Hatfield, the workers simply continue building. Women sand the plywood skins to mirror finish. Carpenters from local piano factories shape bulkheads with the precision of instrument makers. Each fuselage half is cured in heated molds for 20 hours, then joined along the spine. Every line is smooth, seamless, and aerodynamic. The resulting shape, slim nose, narrow wings, twin tail fins, gives the illusion of fragility. When viewed in motion, however, the illusion breaks. The Mosquito accelerates faster than any RAF aircraft of its size. Observers note how it climbs through low cloud layers without visible strain. The Air Ministry engineers, once dismissive, begin sending requests for further trials. By March 1941, the toy plane, as some pilots had called it, now holds the fastest recorded climb rate of any Allied aircraft. It has no armor, no gunner, no metal fuselage, only speed, silence, and precision. According to later records in the de Havilland archives, the first test flights at Hatfield shifted British aviation's focus from mass to momentum. The engineers had not built a traditional bomber. They had built a philosophy, one that used absence, not addition, as its defense. By April 1941, the flight test reports circulate through Whitehall under the coded heading Prototype W4050, Speed Evaluation. Each page carries a quiet contradiction: a bomber that climbs like a fighter, turns inside its own wingspan, and flies so fast that the standard radar units of the chain-home system struggle to lock onto it. Engineers at the Telecommunications Research Establishment record echoes that flicker and vanish before a full pulse can return. The wooden skin, coated in smooth resin and devoid of metal joints, reflects less signal than any aircraft previously observed. At Hatfield, the prototype undergoes performance trials at altitude. The pilot levels out at 20,000 feet, throttles open. The Merlins hold steady at 3,000 revolutions per minute, their synchronized hum cutting through the air with precise symmetry. Ground observers time the pass with a chronograph and confirm an average speed of 400 miles per hour. The figure is reported without commentary, only an asterisk, verification pending. The number alone challenges the RAF's own classification tables. De Havilland, characteristically calm, submits the results to the Air Ministry with a single line of explanation: speed as defense validated. The phrasing is deliberate. No exaggeration, no claim of superiority, just data aligned with an argument made months earlier in the design phase. The aircraft's strength lies not in resistance but in avoidance. At the same time, the British production system faces material strain. Aluminium remains under allocation for Spitfires and Lancasters. The Mosquito's reliance on timber allows dispersed manufacture across civilian furniture and piano factories. At a facility in High Wycombe, carpenters trained in cabinet-making plane wing spars to tolerances of thousandths of an inch. Women at a coachworks in London apply glue by brush, 2 inches wide, measured by habit not by gauge. The simplicity of the design becomes its resilience. Operational demand begins to shift. Intelligence intercepts from occupied France describe faster reconnaissance aircraft appearing over coastal installations, small, twin-engined, unarmed, and unreachable. German observers record them as light bombers, possibly wooden. Luftwaffe pilots, dispatched to intercept, find only vapor trails fading into cloud. Post-war German reports later note the same phrase: target disappeared into haze at high speed. Contact lost. Within the RAF, skepticism gives way to calculation. Bomber Command Statistical Section compares fuel consumption, production time, and sortie range. The Mosquito completes missions with half the crew, half the material cost, and double the survival rate of conventional aircraft. Its design contradicts nearly every wartime assumption about what a bomber should be. Yet the numbers hold. During one recorded evaluation at Boscombe Down, an RAF officer describes the aircraft's acceleration during low-level approach. His tone, captured on magnetic wire, remains matter-of-fact, no vibration through the stick. Feels lighter than weight suggests. Climbs clean. Responds instantly. Hard to believe it carries a full bomb load. The tape clicks off, leaving static. That recording, filed under Flight Test number 214, becomes the first-hand account of the Mosquito's defining characteristic, effortless speed achieved through minimalism. The breakthrough spreads quietly. By late 1941, the ministry approves limited production runs under Category B. De Havilland's engineers refine the assembly molds, adjusting curvature and bonding pressure. Each test confirms what intuition had already shown: the birch-spruce composite absorbs stress without permanent deformation. The wooden frame, once viewed as fragile, now registers superior fatigue resistance compared to riveted aluminum. The first operational Mosquitoes deploy in reconnaissance roles. Their cameras capture enemy coastal positions with clarity unmatched by earlier aircraft. Crews return hours ahead of schedule, reporting no interception attempts. Intelligence officers note the trend with increasing precision. By the end of the year, interception probability drops to near zero. German radar reports continue to describe the aircraft as phantoms. The transformation is almost invisible, taking place not through a single dramatic success but through accumulation of data, sortie times, altitude consistency, fuel margins. Each line in the logbooks draws the same conclusion: the wooden aircraft performs beyond theoretical limits. The evidence no longer needs advocacy. It exists, repeatable and measurable. At Hatfield, production expands. The hangars hum late into the night, sawdust mixing with the smell of glue and warm metal. De Havilland walks the floor quietly, stopping to run his hand along the curve of a finished fuselage. The wood is warm from the curing lamps, the surface flawless. Around him, engineers discuss weight distribution, not philosophy. The aircraft has proven its point. What began as an experiment has become a strategic asset. According to wartime memoranda later released by the ministry, it was during these weeks that the RAF first recognized what it had built: not merely a new bomber, but a new principle. The Mosquito's wooden frame had changed the arithmetic of air war, replacing armor with velocity and mass production with precision craftsmanship. Summer 1941. The results are on paper, but belief lags behind. Inside the Air Ministry's austere offices at Whitehall, rows of wooden filing cabinets hold reports stamped "Confidential, Experimental Aircraft Division." Between them, men in uniform exchange clipped remarks about priorities, tonnage, and risk. The Mosquito's flight records are accurate, but the aircraft itself remains an anomaly: too light, too fast, too different from the doctrine that shaped British bombing strategy since 1936. The minutes of one meeting, held on June 4, record a familiar phrase: a wooden bomber is no substitute for armor. The sentiment comes from Air Marshal Sir Wilfrid Freeman, who nonetheless had approved the prototype months earlier. Even he struggles to persuade others that speed can replace guns. The Bomber Command representatives argue for consistency, large crews, multiple defensive turrets, formation tactics. The Mosquito, they insist, breaks every established rule. At Hatfield, the engineers receive these hesitations as silence. Orders slow. Funding arrives in intervals. The assembly line continues only through private contracts and de Havilland's own reserves. In the drafting office, pencil marks fill blueprints that may never see production. The workers keep sanding, keep gluing, keep pressing the curved shells into shape, because stopping would mean admitting failure. Test pilot Geoffrey de Havilland Jr. flies another trial before a skeptical audience of senior officers. The takeoff is unremarkable. The climb smooth. Then he pushes the throttle to maximum, levels out, and vanishes into the thin clouds. A full minute later, the sound of the engines returns, a low roar that crosses the airfield before anyone can track it. When he lands, there is no applause, only note-taking. One officer remarks that it looks too fragile to survive operations. Another suggests the aircraft might be used for training or light transport. Behind closed doors, de Havilland argues that the Mosquito's purpose is not replacement, but revolution. It can go where others cannot, he says in measured tone. It reaches target and returns before opposition can form. His reasoning is met with polite acknowledgement, then deferred. The RAF strategy remains built on durability, not velocity. By August, production of heavy bombers drains all available metal. The Mosquito's use of timber is noted in supply reports, but still treated as a curiosity. Yet necessity begins to shift opinion. Reconnaissance units request faster aircraft to photograph enemy defenses ahead of the coming raids. The Spitfires lack range, the Blenheims lack altitude. The Mosquito fits both needs, even if the decision-makers hesitate to admit it. An internal memo from the Directorate of Technical Development, dated September 10, carries a reluctant endorsement. D.H.98 Mosquito may serve in specialized reconnaissance capacity. Limited order to follow. The tone is bureaucratic, but it marks the first official recognition that the aircraft's performance cannot be ignored. At Hatfield, the news is met with quiet relief. Workers redouble their pace. Plywood arrives from Canadian mills, casein resin from laboratories in Slough. The furniture factories in High Wycombe begin to hum at night under blackout curtains, their craftsmen turning from tables to wings. The same tools that once shaped cabinetry now define the contours of flight. The transition from doubt to acceptance happens gradually. Reports from initial reconnaissance missions begin to circulate. Crews return unharmed, often hours earlier than expected. One flight from RAF Benson to Kiel photographs naval docks and returns without interception. The photographs show anti-aircraft crews still at their posts, unaware they had been overflown. At the Air Ministry, the pattern becomes statistical. Every sortie completed without loss undermines old assumptions. Commanders begin to view the Mosquito less as an oddity and more as an insurance, a tool for missions too dangerous for slower aircraft. In a small meeting room off the main corridor, an intelligence officer lays a single photograph on the table, the port facilities at Wilhelmshaven, clear and undistorted, taken from 25,000 feet. He points to the margin where German radar masts are visible, their shadows long on the ground. They never saw it coming, he says. The others nod but say little. No one writes the word success. The Air Ministry prefers understatement. By the end of the year, the Mosquito receives formal classification as a high-speed bomb reconnaissance aircraft. Production scales modestly, but the principle has crossed the threshold from curiosity to necessity. The wooden airframe once considered impractical now stands as the only platform that can operate over occupied Europe without escort. In the quiet of Hatfield's assembly hall, the shift feels almost invisible. The same benches, the same sawdust, the same faint hum of engines under test. Yet the tension in the air has changed. The aircraft that began as an experiment now exists because it must. The war has no room for disbelief. February 27, 1942. The airfield at RAF Whiten lies under low cloud and thin rain. Two Mosquitoes stand at the edge of the runway, engines ticking over, wings shining with moisture. Ground crews move quickly, tightening cowling bolts and wiping condensation from camera lenses. Each aircraft carries 500-pound bombs inside a slim internal bay. No defensive guns, no escort. The crews are briefed to fly alone, at treetop height, across the North Sea toward Oslo. The objective is precise: strike the Gestapo headquarters in the center of the city at noon. Inside the operations hut, mission timing is synchronized to the second. The aircraft lift off at 10:29. Their silhouettes vanish within minutes into the gray horizon. At their cruising altitude, barely 50 feet above water, the altimeters tremble. The pilot holds steady, eyes fixed on a single line of compass and coastline. The navigator plots minute adjustments, counting river bends and forest clearings as markers. Their radios remain silent. The Mosquito's twin Merlins hum in perfect unison, the wooden frame resonating like a tuned instrument. Over the North Sea, the wind rises. The aircraft slice through it cleanly, their varnished fuselages shedding spray. At these speeds, control depends on precision. A single misjudgment means impact. Yet both aircraft maintain formation through instinct and trust in the machine. At 12 o'clock local time, the pair appear over Oslo. Anti-aircraft guns fire almost immediately, their shells bursting high and behind. The Mosquitoes drop their bombs from less than 200 feet. The impact is instantaneous, windows shatter across the city center, the target building collapses inward. In the confusion, the aircraft climb sharply and turn for home. Their speed carries them beyond range before the enemy can correct aim. The mission lasts for hours and 50 minutes. Both aircraft return to base without damage. The after-action report, typed in clear capitals, records the essential facts only: objective destroyed. No casualties. No interception. There is no comment on design or theory. Yet in those 3 lines, the aircraft's purpose is proven beyond debate. Within days, the Air Ministry revises its assessment. The Mosquito is reclassified as a multi-role strategic bomber. Orders increase. The skepticism of earlier months dissolves under measurable results. Combat footage from nose-mounted cameras shows the aircraft's stability during attack runs, smooth, unwavering, unaffected by flak bursts. Intelligence officers analyze the film frame by frame, searching for vibration or structural flex. None appear. Over the next weeks, Mosquitoes conduct raids on Cologne, Aarhus, and The Hague. Each mission follows the same pattern: low entry, rapid strike, clean exit. German defenses respond too late. Luftwaffe radar operators describe fast twin-engined intruders crossing detection grids faster than pursuit calculations allow. Fighter controllers scramble Mi-109s and FW-190s, but the Mosquitoes vanish before visual contact. By the time interceptors reach operational altitude, the British bombers are already over the channel. At RAF Benson, reconnaissance squadrons adapt the same airframe for photographic work. Cameras mounted in the bomb bay capture images at 30,000 feet. The clarity astonishes analysts. Power stations, rail yards, and U-boat pens recorded in perfect resolution. Crews report missions completed without a single engagement. "They can't touch us," one pilot remarks in a recorded debrief, his tone neither triumphant nor emotional. It is a statement of fact. The transformation in strategy becomes visible across the command structure. The Mosquito's performance allows daylight raids previously deemed impossible. Targets once reserved for heavy formations can now be struck by 2 aircraft operating alone. Precision replaces saturation. The shift is mathematical: fewer bombs, more accuracy, less loss. In early 1943, the Mosquito performs its most symbolic test. 11 aircraft are assigned to strike the prison walls at Amiens, cutting a breach for French resistance captives. Flying at less than 100 feet through fog and snow, they reach the target undetected. Bombs fall in sequence, walls collapse, escape begins. The leading aircraft is hit but returns on one engine, its wooden frame scorched yet intact. The mission's code name, Operation Jericho, enters the archives as proof that speed and precision can achieve what weight and armor cannot. At Hatfield, production expands beyond capacity. New factories open in Leavesden and Chester. Supplies of plywood arrive from Canada and New Zealand under naval escort. Furniture firms across Britain now build wings instead of wardrobes. The nation's craftsmanship converges around a single idea, the wooden plane that outruns death. Back at the Air Ministry, the tone of correspondence changes. Reports no longer question the Mosquito's durability or purpose. Instead, they track performance increments, engine power, altitude ceiling, bomb load. The aircraft once dismissed as impractical now forms a pillar of RAF operations. In a later interview recorded after the war, de Havilland described those first missions with the precision of a craftsman recalling a finished piece. "We built it light because we had no metal. It turned out faster because of that." The words are plain, but behind them lies the quiet validation of a design born from necessity, proven in the open sky, under fire, by nothing more than its own speed. By mid-1943, the numbers begin to speak louder than any argument. Operational summaries from Bomber Command show that Mosquito squadrons fly more sorties per aircraft than any other Allied bomber in service. Each machine averages 3 missions per week, twice the rate of a Lancaster. Losses remain below 2%, compared with more than 6 for heavy formations. Fuel consumption per ton of explosives delivered is less than half that of a Halifax. In the war's arithmetic of efficiency, the Mosquito stands alone. At the Ministry of Aircraft Production, analysts compile comparative charts. They note the absence of gunners, armor, and redundant systems. Where a heavy bomber requires a crew of 7, the Mosquito flies with 2. Its structure, built from thin laminates of birch and spruce, allows greater internal space for payload relative to weight. In effect, it carries more bomb per pound of airframe than any other aircraft of the war. These are not superlatives, they are ratios printed in black ink across supply ledgers. Reports from operational units confirm the data. Number 105 Squadron records a sequence of 73 missions without a single loss to enemy fighters. Reconnaissance squadrons, flying deep over Germany, report detection only when descending below 15,000 feet. The smooth wooden surface reflects radar so poorly that ground operators often mark returns as weather interference. Engineers at Farnborough conduct controlled experiments, suspending fuselage sections in front of radar dishes. Readings vanish into static. The findings are logged under the term low reflection composite, an expression decades ahead of its eventual recognition. In practical effect, the Mosquito has become invisible, not by intention, but by material coincidence. The same properties that made it light also made it elusive. German night fighter crews describe seeing flashes of exhaust in the dark, then nothing. Gun camera footage from interceptors shows bursts of fire at empty sky. The Mosquito's speed and radar resistance create a new kind of warfare, one where absence itself becomes a weapon. Within Britain, production statistics expand across multiple industries. Over 400 subcontractors supply components. Piano factories build fuselage frames, coach builders fabricate wing spars, joinery shops in Wales produce wooden ribs by hand. Women compose more than a third of the workforce, their precision shaping each joint and curve. The aircraft's quality control sheets show rejection rates under 2%, an industrial miracle under wartime conditions. The ministry's financial tables record another quiet revolution. The total cost of one Mosquito equals roughly a quarter of a Lancaster's. Yet its operational effect, measured in target accuracy and mission survival, exceeds expectation by wide margins. Every figure reinforces the same conclusion: speed and simplicity yield greater return than mass and complexity. In operational theaters, these abstractions translate into survival. Crews flying Mosquitoes over Berlin describe the peculiar silence of their missions. At 400 miles per hour, the aircraft reaches the target before searchlights can align. Bombs fall, photographs record impact, and within minutes the aircraft is already returning over the North Sea. Debrief reports from those flights are brief, almost terse. No contact. Target confirmed. Landed 0405. The brevity itself becomes evidence of efficiency. By late 1943, the Luftwaffe's countermeasures escalate. Specialized units equipped with radar-guided night fighters attempt interceptions. Even then, success remains rare. The Mosquito's climb rate, exceeding 3,000 feet per minute, allows it to escape through cloud layers before contact. One German pilot, interviewed after the war, compared it to trying to catch a shadow across the moon. Inside de Havilland's design office, engineers continue measuring each variable. Flight logs, fuel curves, structural fatigue records, all confirm a stability that seems improbable for a wooden aircraft. Stress tests show that the birch spruce sandwich construction endures 11 G loads before deformation. The adhesive bonds, once doubted, prove stronger than the wood itself. During destructive testing at Salisbury Hall, the fuselage breaks not at the glue lines but through solid timber. The data is signed off with a single annotation, adhesive integrity complete. The aircraft's psychological impact on both sides is harder to quantify but equally real. British crews trust it with the certainty once reserved for armored bombers. German ground observers report frustration bordering on disbelief. The enemy radar screens, once symbols of control, now betray uncertainty. In this sense, the Mosquito changes not only the physical balance of air war but its logic, a shift from endurance to evasion, from armor to invisibility. By December 1943, Bomber Command issues an internal directive acknowledging the aircraft's unique contribution. The Mosquito represents a separate category of warfare, precision by velocity. No fanfare accompanies the phrase. It appears only once, buried among tables of figures. Yet in those words lies the formal recognition of what Hatfield's carpenters, designers, and pilots had already demonstrated in the air. In the factory canteens, production crews read fragments of these reports reprinted in local newspapers. They know little of radar equations or sortie ratios, only that their work keeps returning intact. Each completed fuselage leaves the hangar smelling faintly of glue and polish, a wooden shape that statistics now call indispensable. Winter 1943. The hum of production stretches far beyond Hatfield. Across Britain, in small towns and converted workshops, the Mosquito takes shape piece by piece. A carpenter in High Wycombe planes the edge of a wing spar under a single overhead lamp. The smell of pine oil and glue fills the air. His tools are the same he once used to build cabinets, now turned to the precise tolerances of flight. The measurements come not from blueprints alone but from muscle memory, the instinctive pressure of hand and blade passed from trade to trade. At Leaves Den, the main assembly line runs day and night. The rhythm is methodical, sanding, gluing, pressing, curing. Women in headscarves lift preformed fuselage halves into heated molds where temperature and pressure are controlled by stopwatch and feel. Casein and urea-formaldehyde resins are brushed onto birch veneers in thin layers, their smell sharp and chemical. Once the molds close, the plant grows silent except for the hiss of steam. In 12 hours, the shells emerge hardened, light, and seamless, smooth enough to reflect the overhead lights like glass. The wooden halves are joined with a single adhesive seam down the spine, reinforced by internal bulkheads of spruce. Each joint is tested by tapping with a mallet, a dull sound means rejection. Inspectors move down the line with stethoscope-like listening tubes, identifying hollow spots that betray trapped air. Even in wartime haste, quality control remains absolute. The material may be wood, but the tolerances are those of metal. Supplies arrive from every corner of the Commonwealth. Birch from Canada, spruce from British Columbia, mahogany for jigs from West Africa. Rolls-Royce engines come by rail under camouflage tarps. In one factory near Chester, workers glue layers of balsa between sheets of birch, forming lightweight sandwich panels for the tailplane. The panels are stacked in long rows, marked with chalk numbers, then sent by lorry to final assembly. The war has turned industry into network. A former piano factory in London builds instrument panels and control columns. A boatyard in Norfolk shapes engine nacelles. A furniture firm in Buckinghamshire produces the intricate curves of the nose cone. None of these places were designed for aviation, yet together they form the spine of Britain's most advanced aircraft. The system is invisible to bombing raids, dispersed, adaptable, self-sufficient. Inside the Hatfield design office, draftsmen update blueprints on tracing paper worn thin by use. Each revision simplifies production, fewer parts, faster assembly. The Mosquito evolves not through invention but refinement, its complexity hidden beneath smooth lines. De Havilland walks the shop floor in a heavy coat, notebook in hand, recording small adjustments. He speaks quietly to foremen, rarely raising his voice. The tone of the factory mirrors its product, precise, restrained, efficient. Power shortages and rationing bring improvisation. Steam presses are run on coal collected from dismantled chimneys. Glue mixtures are warmed with electric irons when boilers fail. Crews work through air raids, blacking out windows with felt. The factory lights dim, but the sound of hand planes and mallets continues in rhythm. The war cannot wait for daylight. Each completed fuselage receives a thin coat of aluminum-colored lacquer, deceptive at a distance. From above, the aircraft appears metallic, camouflaged by illusion. Underneath, the surface remains pale wood, sealed against moisture by shellac and resin. Before shipment, inspectors stamp the serial number onto the internal bulkhead and record the total man-hours. The figure varies slightly but averages 1/3 that of a comparable metal aircraft. When the parts converge at the final assembly hangars, the atmosphere shifts from workshop to orchestra. Crated fuselage halves arrive from one region, wings from another, tail sections from a third. Teams work with synchronized precision, attaching engines, instruments, and armaments. The air smells of fuel and polish. Mechanics test hydraulics, check fuel pressure, and align propellers by eye. There are no excess movements. Every gesture counts. Visitors from the Air Ministry, touring the line for the first time, are struck by the absence of noise. No hammering of rivets, no sparks, only the quiet scrape of sandpaper and the low hiss of steam. It feels more like a joinery school than a war factory. Yet the output is military efficiency, one completed aircraft every 4 hours. Outside, finished Mosquitoes wait under camouflage nets, wings glinting faintly in the weak sun. The smell of glue mingles with the exhaust of trucks hauling fresh timber to the loading bays. From a distance, the scene could be mistaken for a furniture depot, yet each crate and spar carries the geometry of flight. A production foreman writes in his logbook, "This is what we have. Wood and skill. Enough." The sentence captures the essence of the enterprise, a war machine built not from steel but from discipline, precision, and craft. By spring 1944, Britain has produced over 1,000 Mosquitoes through this distributed network. None are identical, yet all perform within the same exacting limits. The design tolerates human variance because it was conceived in it. A machine of wood, shaped by hands, guided by numbers. The war has transformed carpenters into engineers and workshops into armories, proving that technology is not the property of material but of method. At Salisbury Hall, north of London, the heart of the Mosquito's engineering story lies not in a hangar but in a converted country house surrounded by meadows and streams. The building itself looks domestic, brick walls, ivy, and a gravel drive, but inside, drafting tables line the rooms where carpets once lay. Here, engineers work through equations on graph paper yellowed by tobacco smoke. Every calculation converges on one question: how can wood, a living material, withstand the dynamic stresses of flight beyond 400 miles per hour? The answer is geometry and chemistry. The Mosquito's fuselage is not built of simple planks or ribs but of a true monocoque shell. 2 layers of birch veneer are glued over a core of end-grain balsa wood, a lightweight filler arranged like a honeycomb in natural form. Each layer is set at alternating grain directions to distribute tension. When bonded under heat and pressure, the composite behaves as a single continuous curve, transferring load across the skin rather than through internal frames. What appears fragile in the workshop becomes, in structure, stronger than riveted aluminum. To test this, engineers construct a full-scale fuselage section and mount it between steel clamps. Hydraulic pistons apply pressure along the longitudinal axis, replicating the stress of a high-speed dive. At 9 gs, the wood creaks but does not split. At 10, the outer veneer begins to whiten under compression. At 11, a sharp crack runs through the balsa core, but the adhesive seam holds. The test rig operator notes the point of failure in a calm voice. Fracture through material, not joint. The record shows adhesive strength exceeding the wood itself, a first in aviation. The resin used for bonding is a urea formaldehyde compound refined at the Royal Aircraft Establishment. When mixed, it emits a faint acidic odor, sharp enough to sting the eyes. Once cured, it becomes translucent, nearly invisible between veneers. Chemically stable, waterproof, and heat-resistant, it transforms carpentry into engineering. Casein glue, made from milk proteins, is still used in secondary joints, but the critical seams depend on the new synthetic resin. In production notes, de Havilland's chief chemist calls it an invisible rivet. Wing construction follows the same logic. Each half-wing is built as a single box spar, 2 birch webs and spruce flanges, reinforced by plywood ribs. The structure tapers outward, maintaining stiffness with minimal weight. When mounted on the fuselage, the wings and body form one aerodynamic surface, uninterrupted by protrusions. Airflow stays laminar longer, reducing drag and cooling the engines more efficiently. In wind tunnel trials at Farnborough, this smooth continuity proves decisive. Drag coefficients fall by nearly 20% compared to the Blenheim, despite carrying twice the power. Engineers at Rolls-Royce collaborate closely, modifying the Merlin's carburetors to deliver steady fuel flow during negative G maneuvers. The result is instantaneous throttle response. Combined with the Mosquito's low mass, it grants acceleration unseen in twin-engined aircraft. In test dives, the airspeed indicator passes 430 miles per hour before leveling. The wooden skin, sealed under lacquer, remains smooth under the stress of compressibility, no buckling, no oil canning. Heat presents a subtler challenge. Wood insulates, engines radiate. The solution lies in vent design. Each nacelle incorporates narrow slots along the cowling edge, channeling airflow through the radiator matrix and out beneath the wings. Thermocouples record consistent temperature even at full power. The data confirms thermal equilibrium across the structure, another victory of observation over assumption. In one experiment, engineers attach small metallic sensors to the fuselage and wings to measure vibration harmonics during flight. The readings show that the wooden structure dampens oscillations faster than aluminum. Instead of amplifying resonance, it absorbs it, giving the Mosquito its distinct quietness in flight. Pilots later describe the cockpit as serene, though the term never appears in official documents. Every problem solved in wood teaches a broader principle. When metal is scarce, understanding replaces material. When rivets cannot be hammered, molecules must be aligned. The Mosquito becomes a study in what can be achieved through precision rather than abundance. In late 1943, visiting engineers from the United States Army Air Forces tour Salisbury Hall. They examine the molds, the adhesives, the curved sections under test. One asks how the structure maintains tolerance across so many wooden parts. De Havilland's deputy simply replies, by not cutting corners. The visitor records the phrase verbatim in his notebook. Outside, under a tarpaulin, sits a stripped fuselage shell waiting for analysis. The surface catches the light, pale and flawless. From a few feet away, the grain of the birch is visible, lines of nature transformed into lines of force. Every fiber holds tension, every seam direction follows airflow. Nothing is decorative, everything is functional. By the end of the year, engineering data confirms what pilots already feel: the Mosquito's strength is not in armor or mass, but in harmony. Material, design, and purpose align until the aircraft ceases to behave like wood or metal and begins to behave like air itself. By early 1944, the Mosquito's airframe has become a platform rather than a single design. Its core remains the same, the smooth birch spruce monocoque, but the configurations multiply. What began as an unarmed reconnaissance aircraft now divides into categories marked by brief codes: B for bomber, PR for photo reconnaissance, NF for night fighter, FB for fighter bomber. The letters change, the silhouette does not. Each version answers a new demand from a war that keeps changing its shape. At Hatfield, the drafting office reconfigures the internal layout for armament. The clean nose of the original bomber gives way to a solid wooden block fitted with 420mm Hispano cannons and 4.303 Browning machine guns. The weight increase is marginal, the airframe absorbs it easily. Ammunition belts run along the fuselage like veins beneath the skin, unseen once the panels close. The resulting aircraft, the Mosquito FB.VI, emerges as one of the fastest armed planes of the war, capable of both precision strike and pursuit. Night fighter variants follow. Engineers fit the nose with radar sets developed at the Telecommunications Research Establishment. The equipment, known as AI-Mk8, sits behind a black-painted perspex dome that alters the aircraft's expression but not its aerodynamics. In the dark over Britain, the radar pulse travels invisibly ahead of the aircraft, searching for bombers. When contact is made, the pilot maneuvers by instrument alone, guided by the calm voice of a navigator interpreting green blips on a cathode screen. The twin Merlins drone at constant pitch, the wooden fuselage dampens the vibration so completely that crews describe it as flying inside a musical instrument. In its new role, the Mosquito becomes the hunter. German bombers crossing the channel find themselves pursued by shapes they cannot see. Night after night, reports from Luftwaffe crews mention sudden tracer fire from behind and the brief silhouette of twin tail fins disappearing into the black. The British ground stations note interceptions completed within minutes. The statistics show a single Mosquito destroying more enemy aircraft per sortie than any other night fighter in service. Meanwhile, the photo reconnaissance units expand their operations over Europe and the Baltic. These aircraft fly unarmed and unpainted, their pale wood sealed under clear lacquer. At 35,000 feet they cruise faster than the Spitfire, cameras angled through the bomb bay. From those lenses come the images that guide nearly every major Allied raid of the later war: docks at Kiel, the rocket sites at Peenemünde, the synthetic fuel plants at Luna. The photographs are so sharp that analysts can measure the length of rail cars and the direction of shadow. Crews return without interception, their reports as brief as their missions: weather fair. Objective covered. Home safely. As the variants multiply, production lines adapt in kind. The same jigs and molds produce both bombers and fighters, only the internal fittings differ. The process reflects the airframe's flexibility. Every design element, weight distribution, access panels, electrical routing, was conceived from the start to allow change. When the RAF requests a high-altitude pressurized model, engineers fit a sealed canopy and oxygen system without altering the basic structure. The wooden shell accepts modification as if anticipating it. In Germany, intelligence analysts study captured fragments from crashed Mosquitos and remain puzzled. Reports describe unusual materials of non-metal composition. Metallurgists test the pieces and find no alloy at all. One memorandum from the Luftwaffe's technical office admits, almost reluctantly, that the English have achieved speed through materials unsuitable for industry. It is not a compliment, it is recognition of failure to imitate. On the ground, in occupied Europe, civilians look up to see a blur crossing the sky without engine note until it is already gone. Railway depots, radio stations, and administrative buildings suffer sudden precision strikes, followed by silence. Propaganda broadcasts refer to the attacker as the wooden wasp. The name, though intended as mockery, spreads among RAF crews with quiet pride. By the spring of 1944, the Mosquito exists in more than 24 operational forms. Fighter bomber strafe trains in France ahead of the Normandy landings. Night fighters patrol the skies above London, guiding by radar and moonlight. Reconnaissance crews photograph the Rhine bridges hours before paratroopers cross them. The aircraft shifts between roles without pause, its identity defined not by its structure but by its adaptability. At de Havilland's headquarters, engineers keep a tally of variants on a chalkboard near the main entrance. The numbers climb weekly. Each new configuration adds proof to the same idea, that one frame, built from wood and logic, can answer every demand of war. Late one evening, Geoffrey de Havilland stands beside a newly completed night fighter under inspection lights. The black paint dulls the curves, only the propeller tips glint. A ground crewman tightens the last cowling bolts. De Havilland touches the fuselage briefly, as though confirming that the material still holds truth. Around him, the hangar hums with quiet certainty. The Mosquito has ceased to be an experiment. It has become an ecosystem of speed, invisibility, and adaptation. By late 1944, the Mosquito had become a recurring ghost in German air defense reports. Radar operators along the western coast logged fast-moving contacts that appeared and vanished within seconds, crossing entire sectors before tracking systems could fix their altitude. Controllers at the Kamhuber line, the night defense network stretching from Denmark to France, described the aircraft as unclassifiable, too small for a bomber, too fast for a reconnaissance plane. In the daily summaries of the Luftwaffe's Jagddivisionen, one phrase appeared again and again: Blitzflugzeug unbekannter Bauart, lightning aircraft of unknown construction. In the radar bunker at Stade, operators watched their scopes in frustration. The long green sweeps of the Würzburg and Liechtenstein screens showed echoes flickering like static. Sometimes a trace would surge toward Berlin at impossible speed, then vanish over the city. Commanders dispatched night fighters on interception vectors, but contact rarely occurred. A few pilots claimed visual sighting, twin engine, silver finish, no guns, followed by a steep climb and disappearance into cloud. Others fired at contrails they could not close with. To counter this phantom, the Luftwaffe reorganized special pursuit squadrons. Aircraft such as the Ju-88 G6 and Me-10 were fitted with advanced radar and boosted engines. Yet even these found the Mosquito's margin unreachable. The German fighters could climb higher, perhaps, but never fast enough to overtake. The Mosquito's combination of low radar cross-section and pure velocity made interception a problem of physics, not skill. Records from the German radar experimental site at Rechlin note repeated attempts to track the wooden aircraft. Engineers altered transmitter frequencies, strengthened pulse power, even coated antennas with anti-static compounds to refine detection. The results remained erratic. The Mosquito's wooden frame and resin skin absorbed rather than reflected the radio energy. Reflections came from engine nacelles and propeller hubs only, too small, shifting points too narrow for consistent range. When the operators increased gain to detect these traces, the screens filled with noise. They are invisible until they attack, one report concluded. Then it is too late. The aircraft's psychological effect reached beyond the radar rooms. By 1944, Mosquito bombers conducted daylight raids on Berlin itself. Flying at high altitude, they struck Gestapo offices, radio transmitters, and railway command posts with uncanny precision. Alarms sounded, sirens wailed, and by the time anti-aircraft batteries adjusted, the bombers were gone. The entire attack lasted minutes, leaving only scattered fires and confusion. Goebbels' ministry forbade newspapers from naming the aircraft. Internal correspondents called it the terror from nowhere. Pilots of the Luftwaffe's night fighter wings later recalled the demoralization it caused. You would take off on alert, and by the time you reached altitude, the raid was over, wrote one veteran of NJG-1. You never saw them. You heard of them. Another compared the sound to a whisper crossing the sky, brief, directionless, final. Attempts to lure the mosquitoes into traps also failed. Radar controllers created false corridors of radio beacons, hoping to mislead British crews into predictable paths. But the navigators, guided by dead reckoning and starlight, ignored them. Their aircraft crossed Germany as if following invisible lines only they could see. At Peenemünde, during the testing of the V-2 rockets, Mosquito reconnaissance flights captured detailed images of launch platforms from 30,000 feet. The Luftwaffe dispatched interception groups specifically to protect the site. On August 17, 1944, two Bf-110s climbed to meet an incoming Mosquito pair. The German radar confirmed contact. Within 3 minutes, both enemy blips disappeared. The German fighters reached altitude but saw nothing. The British aircraft had already completed their pass and returned to the Baltic coast. In post-war interrogations, German radar specialists conceded the futility of countering a target that violated every assumption of their system. The reports read less like confession than resignation. It was too small to see, too fast to hit, too few to stop. Some even admired the precision. They flew as if they owned the air, one officer told Allied debriefers in 1945. For the British crews, this invisibility was never arrogance, only arithmetic. The Mosquito's speed and material properties created an envelope of safety no other aircraft could offer. Its pilots operated in calm efficiency, executing missions under conditions that made defense irrelevant. The Luftwaffe could adapt its tactics, but not the laws of reflection and velocity. In the intelligence files compiled after Germany's surrender, one section bears the title Countermeasures Ineffective. It lists every attempt: improved radar, heavier flak, dedicated interceptors, followed by a single outcome: failure. The final line of the report reads without embellishment: the Mosquito remained largely immune to interception until the end of hostilities. By then, the ghost of the wooden plane had crossed every German city, every defensive zone, and every technological boundary that sought to stop it. The enemy's response had become a record of futility, preserved in logbooks and radar tapes, a precise measure of how invisible a simple idea could become when perfectly executed. By spring 1945, the Mosquito's presence is everywhere and nowhere at once. It has no single front line, no defining battle. Instead, its influence threads through the daily arithmetic of war: tonnage delivered, sorties completed, losses avoided. The figures recorded at Bomber Command Headquarters in High Wycombe form a quiet monument in numbers. Over 30,000 sorties flown. 45 million miles logged. An operational loss rate consistently below 2%. In a conflict measured by attrition, the Mosquito's survival ratio borders on the improbable. The aircraft's flexibility reshapes Allied planning. When heavy bomber formations of Lancasters or Halifaxes require precise marking for night raids, Mosquito pathfinders lead them in, dropping flares at exact coordinates. Where radar jamming and deception are needed, Mosquitoes carry a window chaff dispensers, their low radar profile making them ideal for masking entire waves behind them. In daylight operations, fighter-bomber units conduct pinpoint attacks against Gestapo offices, ammunition depots, and rail bridges across occupied Europe, targets once considered too risky for conventional aircraft. At Allied intelligence, the aircraft's reconnaissance photographs begin to replace written reports as the standard form of evidence. From these images, analysts map German fuel shortages, rail disruptions, and unit relocations. The precision of each photograph transforms planning from estimation to measurement. "It gave us sight," one British officer wrote later. "It showed us the enemy as they truly were." The Mosquito's effect on morale is subtler but profound. Pilots returning from missions describe a kind of quiet confidence unknown in the era of mass bombers. They operate in pairs, not squadrons. Their survival depends on discipline, not armor. For many, the aircraft becomes an extension of judgment, precise, responsive, honest. A machine that rewards skill rather than luck. At the same time, the German command structure acknowledges the aircraft's disproportionate impact. Post-war interrogations of Luftwaffe officers reveal frustration bordering on respect. General Adolf Galland, in his memoir, later referred to the Mosquito as the most extraordinary aircraft of the war, no defense against it, no answer to it. The remark carries no bitterness, only recognition of inevitability. From an industrial standpoint, the Mosquito represents an inversion of wartime logic. Most aircraft grow heavier, slower, and more complex as the conflict progresses. The Mosquito grows lighter, faster, and simpler. Its production economy allows Britain to divert scarce metals toward other essential needs. Furniture makers, boat builders, and piano craftsmen, scattered across the country, maintain steady output even during bombing raids that disrupt metal factories. The national economy of skill replaces the economy of scale. By the end of 1944, over 7,000 Mosquitoes have been built in Britain, Canada, and Australia. Each carries the same DNA, wood, resin, logic. Their missions range from the Arctic Circle to the jungles of Burma. In every theater, they perform above expectation. One squadron commander summarized their contribution with restrained clarity: "It was never our strength in numbers. It was our ability to be anywhere before they could respond." In strategic terms, the aircraft alters the tempo of the air war. Heavy bombers depend on mass, the Mosquito depends on timing. Its speed allows the Allies to strike during the gaps between German radar cycles, to hit infrastructure before repairs can begin, to maintain pressure without escalation. Historians later describe this as the transition from attrition to precision, a movement from destroying territory to disabling function. The material itself becomes emblematic of British persistence. Wood, once dismissed as obsolete, now defines the most advanced aircraft in the fleet. The contrast between its humble origin and its performance becomes a point of national pride. In newspapers, editors call it the plane that proved craftsmanship could defeat industry. The phrase never appears in official documents, but it lingers in memory. At the close of hostilities, the final operational summary from the Royal Air Force lists the Mosquito's achievements in a single column of type. Bombing accuracy, superior. Reconnaissance, unrivaled. Loss rate, lowest in service. The last entry reads simply, operational until war's end. In May 1945, as Germany surrenders, Mosquito squadrons fly over the ruined cities they once photographed. Below lies the evidence of total war: steel, concrete, and ashes. Above, a machine made of wood hums quietly homeward through thin clouds. The reports filed that week close with a statement as calm as it is conclusive, performance confirmed under all conditions. Aircraft fulfills all expectations. No ceremony, no sentiment. Only acknowledgement, the Mosquito had changed the meaning of speed, of material, and of survival. Autumn 1945. The war is over, but the airfields remain full. Mosquitoes stand in neat rows under the soft light of peace, their varnished skins fading to a muted silver grey. Engines silent, propellers still, they seem lighter than the machines of war that surround them. Ground crews walk between them with clipboards and tape measures, preparing for decommissioning or transfer. The aircraft that once defined speed is now an artifact, still young, still flawless, already belonging to history. At Hatfield, the assembly lines slow to a stop. The smell of glue and steam fades from the hangars. The women who once worked night shifts on fuselage molds return to their homes. The carpenters who shaped spars and bulkheads reopen furniture shops. Yet for many, the discipline of precision remains in their hands, a quiet imprint of the war's most improbable achievement. De Havilland's engineering team gathers for one final report. The lead designer, Ronald Bishop, places on the table a small cross-section of fuselage laminate, birch-balsa, its edges sealed in resin. He turns it over once, sets it down, and says nothing. Around him, the men who once doubted the concept nod in silence. The data is complete, the proof absolute. The wooden monocoque has done what no metal structure achieved, strength through simplicity, endurance through design. In the years that follow, the Mosquito's influence spreads quietly through the next generation of aircraft. Engineers studying jet fuselages borrow its lesson of smooth continuity, the absence of rivet lines, the integrity of the skin as a single load-bearing surface. The English electric Canberra, the de Havilland Comet, and later even American experimental aircraft carry its ghost in their forms. When composite materials emerge, fiberglass, carbon fiber, epoxy resin, their engineers cite the Mosquito as the first demonstration that strength and weight need not be enemies. In official histories, the Mosquito appears as a statistical marvel. In the memories of those who built it, it remains something closer to a craft. Many of its builders never saw one fly. They worked in isolation, under blackout, assembling parts that only met in flight. Yet they understood its purpose, a machine built from what Britain still possessed, wood, skill, and time measured in urgency. Post-war evaluations from the United States and Soviet Union list the aircraft among the most efficient designs of the 20th century. The American Air Technical Service Command calls it a structural concept decades ahead of its materials. Soviet engineers studying captured examples describe its workmanship as beyond industrial reproduction. Both sides recognize what de Havilland proved, that design intelligence can compensate for material shortage, and that innovation often begins where convention ends. The aircraft itself continues to serve. In reconnaissance, mapping, and meteorological roles, Mosquitoes fly into the 1950s, their wooden shells aging gracefully despite humidity and years of service. One record from Singapore notes a Mosquito PR.34 climbing to 42,000 feet, still the highest altitude reached by a propeller-driven aircraft of its type. Time cannot easily corrode birch sealed in resin. At Salisbury Hall, now preserved as a museum, the prototype W4050 rests under soft lighting. Its skin carries the faint patina of age but no cracks. Visitors walk around it slowly, surprised by its modest size. The fuselage reflects them like a mirror of pale amber. Nearby, a placard displays a single line from de Havilland's wartime memorandum, "Speed as protection." No explanation follows. None is needed. The Mosquito's legacy endures not only in material or design but in idea. It represents the inversion of wartime logic, of victory not of armor but of restraint, not of might but of understanding. When historians later search for symbols of human ingenuity under pressure, they find it here, a wooden aircraft that outran an empire built of steel. In archival film footage, one final Mosquito lifts off from Hatfield for a ferry flight to storage. The camera follows its ascent, the twin propellers drawing thin lines across the sky, the wings catching late sunlight. At 1,000 feet it banks gently, revealing its smooth, seamless body, then fades into cloud. The sound of the engines diminishes until only silence remains. According to post-war production notes, that aircraft never returned to operational service. It was dismantled a year later, its parts used for materials research. Yet in that brief final climb, captured on grainy film, lies the essence of its creation, a machine conceived in scarcity, perfected through discipline, and remembered for proving that even wood, when understood completely, can defy the limits of its age.